This is ELC 131, Circuit Analysis 1, and what we're going to talk about now are harmonics. Harmonics are simply integer multiples of a frequency, and the frequency, usually referred to as the fundamental frequency, is symbolized with F sub O, F subscript 0. And the even harmonics are that fundamental frequency times even integer values. F sub O times 2, F sub O times 4, times 8, etc. And then there are odd harmonics, which are the fundamental frequency multiplied times odd integers. F sub O times 3, F sub O times 5, F sub O times 7, etc. So, for example, if our fundamental frequency is 55 hertz, then the first even harmonic would be 110 hertz. The second even harmonic would be 220 hertz, and so on. The first odd harmonic would be 165 hertz. The second odd harmonic would be 275 hertz. So on the board, I have sketched the waveform for a 55 hertz sine wave, which has a period time or a cycle time of 18.2 milliseconds, and this is sketched in black. And then I've sketched the first even harmonic in red. And note, if you will, that, of course, 2 cycles of the 110 hertz waveform crosses 0 at the same time as 1 cycle of the 55 hertz waveform. So as we continue on in our study of electricity or electronics, especially regarding communications, this harmonics are going to be very important to our understanding of these wave forms, wave shapes that we'll encounter. Now, when we talk about changes in frequency, we're going to use 2 terms here to talk about the change in a frequency from a fundamental frequency. And the first term is the octave. And an octave is simply a change in frequency of times 2. Now, if you've studied music, if you've taken music classes, if you're a musician, you're familiar with this term octave. Octave from octo, which means 8. And on a musical scale, an octave is 8 notes. So, interestingly enough, if we look at the waveforms I had shown up here earlier, that 55 hertz equals a first octave on a musical scale, and 110 hertz equals a second octave on our musical scale. So the change from 55 hertz to 110 hertz is a doubling of frequency, but it's also a change in frequency of times 2. Now, also in looking at changes in frequency, we're going to use the term decade. And a decade is simply a change in frequency of times 10. So from our fundamental frequency, 55 hertz, 1 decade above that is 550 hertz. Now, when we start looking later this semester and in subsequent semesters at filter circuits, these filter circuits will oftentimes be discussed with respect to the change in signal level per octave or decade change in frequency. So these terms will be important later on. Now, another concept we have to understand is the idea of wavelength. And wavelength is simply a measure of how long a waveform is when it travels through space or through a wire. Now, take for example that we have a waveform where the frequency is 100 megahertz. And of course, we would know that the time from here to here would be 10 nanoseconds. That's right. So we know the time associated with this waveform. We know the time associated with one period of this waveform, but if I send this AC signal down a wire, or if I send this AC signal through space in the form of electromagnetic energy, what's the distance associated with one cycle of this waveform? And we assume that electricity will travel through a wire, or electromagnetic energy will travel through space at somewhat near the speed of light, which C equals 3 times 10 to the 8th meters per second. So when we talk about the wavelength of this electrical energy, we use the Greek letter lambda to represent wavelength. So the wavelength of this piece of, or this electricity, this AC waveform, is equal to C divided by F. Wavelength equals the speed of light divided by frequency. So the speed of light, again, is 3 times 10 to the 8th meters per second. The frequency of this waveform is 100 megahertz. And if we divide 3 times 10 to the 8th, we get 3 meters. So if I send this 100 megahertz sine wave through a wire, through a cable, then the distance along that conductor associated with one cycle of the AC energy will be 3 meters. Now, to kind of finish up here, this topic is not so much related to electricity as it is to fun. And I always like to talk about these two terms in this class because quite often we have students that are guitar players, piano players, or other musicians. And to make, correlations between audio energy and electrical energy. So this term pitch, what does it mean? Now, hopefully y'all sat in music class in the 3rd grade or 4th grade, and before you started singing a song, your music teacher would blow on what was called a pitch pipe, so that everyone in the class would know what note to start singing the song on. So pitch to us means frequency. What is the frequency of this acoustical energy as it passes through space? And again, if we're singing or we start singing at an A first octave, which was 55 hertz, now let's change that to A second octave, 110 hertz, we know that the period of this waveform in time is 9.09 milliseconds. So the pitch is merely the frequency of the audio energy, the acoustical energy that hits our ears. Now, the term tone, which is probably more correctly called timbre, and I know it looks like it should be timber, but it's actually pronounced timbre. Timbre is really the wave shape. And I'll ask you, why is it that if I play an A first or A second octave on the piano, it sounds different than A second octave on a saxophone? It sounds different than A second octave played on a flute, different than A second octave played on a trumpet or a guitar. Why do all these musical instruments sound different, even though they're playing the same note? And it's all about wave shape, which is ultimately affected by, guess what? Harmonics. So the flute, the piccolo, the glockenspiel, those instruments are instruments that create a waveform that's very close to a sinusoidal waveform. Now, if we look at the waveform created by a piano playing the same note, the piano would look something like this. Oops, I missed just a little bit. So notice that these two waveforms have the same period, they have the same frequency, they have the same pitch. However, this is more of a complex waveform than that generated by the flute or piccolo. Because when you strike a string on a piano, there's all sorts of harmonics created inside the instrument, and those harmonics are added to the fundamental frequency to give that piano its characteristic tonal qualities, its timbre. Whereas when you play that same note on the flute will be essentially a sine wave because it's just air vibrating through a tube. So again, these terms, pitch and timbre, pitch is the frequency of the waveform, and timbre is the wave shape or the harmonic content of that waveform.